Hello, I'm Court Scherner. I'm the Senior Director of Enterprise Architecture and Emerging Technologies at Progressive Leasing, a virtual lease-to-own company where our mission is to provide simple and affordable purchase options to credit-challenged consumers. Today, I'm excited to talk about the elegant solution that Redis Streams provides to delayed message processing. I've been in technology professionally for a long time, and I've done lots of fun stuff. Most relevant to RedisConf is that I've been using Redis at Progressive Leasing for almost 7 years now, and Redis Enterprise for 3 of those years. If you'd like to talk about how we use Redis or any other fun things to do with great new technologies, please feel free to contact me at the email address shown or through LinkedIn. I'm excited to talk with people who are interested in novel ways to use technology. But let's talk about today's agenda. I'll spend some time talking about the business need. We've been working on finding an elegant solution to delayed message processing for about 5 years, but maybe not every one of you have. And so I'd like to take some time to describe what those needs are. And then we'll talk about some of the other solutions that we've explored, sometimes full solutions, sometimes just POCs or pilots. And then we'll talk about the advantages of using Redis Streams to provide a really elegant solution, a low-code solution. We'll look at our implementation. How do we think about it? How do we construct it? And then we'll actually get into the demonstration and show how an implementation might work. So in a business, we have different systems, especially if you have a services-based architecture like ours. Different parts of the business are doing different things. We have applications and automatic decisioning, etc. And all of these systems are producing events, maybe application complete events and decision events. And the invoice was created and the signature was complete, and then we activated the lease. And then we have a customer communication system that's interested in some of those business events. Depending on what the event is, we'd like to send some kind of communication to the customer, an email or an SMS, or maybe in regulated situations, hard mail. Or for convenience, maybe push notifications, maybe a reminder that your payment is due or that we processed a payment automatically. But for today's conversation, we'll limit our demonstration to just emails. Now, at Progressive, we are interested in what happens when we receive different events. When an application is complete, we like to tell the customer, thank you for the application. And when we've made our decision, we like to tell them, congratulations, you've been approved for $2,000 or whatever the approval amount is. So that's the second email. When they submit their invoice for what they wanted to purchase, we send them an email thanking them for their invoice and reminding them here's how to conveniently e-sign their lease. Now, when they've e-signed, we have to send them a copy of that signed contract, and so we send them an email with that contract attached. And when we finally activated the lease and we're ready to, we've received delivery confirmation or they've walked out of the store with it, we say congratulations, you have an active lease, there's a welcome packet attached, a welcome packet in the mail. Now, 20 years ago, when these things took hours to complete or maybe days to complete, this number of emails was fine. And we weren't sending emails 20 years ago, but certainly in the last 10 years, things have gotten much faster to the point where we can complete the entire process, or the customer can complete the process in 15 minutes. Now, sending all these emails can be confusing to the customer. Our process walks them through each step, and so they'll be in the middle of a signing session when their phone beeps or buzzes or whatever, and they look and say, oh, there's an email from Progressive, and the email says, to sign your lease, click here. And they're maybe confused, well, I thought I was signing it. Is this something different? Is there a different copy that I'm... And so it generates confusion. Ideally, what we like to do is if they complete the entire process in 15 minutes, is to send one consolidated email saying, congratulations, we're happy that we could get you that sectional today. Attached is a copy of the signed document and a copy of your welcome packet, and a hard copy of the welcome packet is in the mail. We also want to send the right email at the right time. Let's say they've submitted their application and we've completed making a decision about how much we'd like to lease to that customer, how much they're approved for a lease, but they haven't done anything in 15 minutes, and so we want to send them an email reminding them about what step is next. The next thing to do is go pick out what you want to buy. And we can include some marketing messaging, like vendor A has some other furniture on sale, etc. Now, I've used some very simple language in this presentation. Our marketing and legal teams have done a much better job of crafting our language and making the emails look nice. But for simplicity's sake, I just wanted to have simple language for these emails. Now, in a traditional event processing system, you have the system that's publishing the messages to some kind of a queue. Maybe it's Redis streams or lists in Redis or RabbitMQ, what have you. And typically, the workers just pop those messages off the queue and process them as quickly as possible. When we want to deal with delayed eligibility, we need something that will delay the eligibility for processing. We need to say these messages are not eligible to be processed for, in this case, 15 minutes. And so in this case, we have a scheduler that's delaying that into some delayed queue, and then the workers can watch that queue. The second need in our case is that if we want the delayed message processing to be series aware, we want it to know that if we receive a decision event before eligibility of processing the application event has occurred, then don't send the email for the application event. Wait until we see the decision event, etc. Then we need both the scheduler and the worker to be aware in some way. And so we need not only delayed eligibility for processing, but series awareness. Now, over the last 5 years, we've looked into these three technologies most heavily. We completed a full implementation into production using Microsoft SQL Server. We used static tables to create the queue, to track what consumers were live and processing which messages and how long they had been out and not acknowledged, and it requires locking messages to make sure who gets which messages. It's quite a complicated process. Part of the complication is that the clients are read-write clients. They're not read-only clients. And so we couldn't take advantage of the scale and the scalability of using read-only shards. And so all in all, this was very heavy maintenance for an implementation. And that's not what we do. While we do innovate on technology as it provides a better customer experience, innovating on a complicated solution for delayed message processing just isn't a high priority for Progressive. And so we deem this too specialized to make it a general purpose system. So we looked into other options. We looked into two POCs with list-based methods using Redis. We wound up with similar concerns as to those with Microsoft SQL solution. We got better performance for sure, but the code base was still complicated and maybe even a little more complicated. And that's certainly subjective, but it seemed more complicated than what we had to do with SQL Server. And then lastly, we did look into RabbitMQ. There's a community module that we tested out. It doesn't have enough support. There's no enterprise backing for RabbitMQ, and the community support wasn't particularly great. This implementation wasn't cluster aware, so there was no HA. So we have a Rabbit cluster, but the delayed messages couldn't be protected by high availability. So that led us to making the decision not to continue with a solution using Rabbit or that module. Now, what about series-aware delayed message processing? Well, the solution that we developed with Microsoft SQL Server was we deemed too fragile to even attempt to add the complexities of series awareness. So we haven't done that with SQL Server. What it boils down to is that with technologies other than Redis streams that we've used in our ecosystem, the solutions boil down to two options. Either you have a highly complex scheduler with a coordinated, highly complex worker that they have to know how the scheduler is scheduling so that they can do their work appropriately. Or you create a highly complex service that's then clustered and highly available that interacts with the original messages coming out of the system. And then the workers interact directly with those services, and they never interact with the queue. Either way, it turns out with other solutions like SQL Server, they're very high code solutions. And I want to say, as I get into talking about the difficulties that we experienced, that the solutions are viable, they work. And there's no reason to believe that anyone did anything wrong, or I don't want this to sound like there's something bad with any of these solutions. I just want to be able to point out how elegant the Redis streams option makes the solution. So let's talk about some of these. Popping messages off of a queue. It leaves no audit trail. The message goes on the queue, then I pop it off, and there's no trail of where that is, who has it, what's in flight, how long has the worker held it, and if the worker fails, how do we recover what was pending? So that's something that we had to build into our SQL Server implementation. And as I said, that got very complicated. High code for the scheduler, high code for the worker. Something that would make this easier to implement would be if we had dynamic queue creation. But as I said, in our case with Microsoft SQL Server, permissions prohibited that, and that's pretty normal for systems. Even in our Rabbit system, with our permissions and our AD integration, that creating new exchanges becomes an admin exercise and not something that we can do on the fly in the code. So that leads us to compromises and more complexities in the data structures and complexities in data access, which leads to complexities in the code. Some of our solutions that we ran up against lacked cluster support. As I mentioned, the Rabbit MQ community module uses a single node, so that's difficult. As I mentioned, also Microsoft SQL Server that doesn't support read-only shards because of our implementation, and maybe you could figure out an implementation with MS SQL Server that would support the read-only shards, but we hadn't. And then you've got delivery management concerns. Standard queues are first come, first served, which makes it easy to figure out who gets the next message. But we also don't know who got the last message. We don't know if that one fails, how do we recover? So that limits flexibility, requires custom message management. And as always, there's performance and reliability concerns. Our concerns with not being able to use the read-only shards led to performance concerns. And as I mentioned with Rabbit MQ's module, there were reliability concerns. But Redis Streams offers more. Built in, we get an audit trail because the entries on the stream are not removed automatically. When we read the stream, we don't remove the entries. We can remove the entries. We want to prune them, and we'll get that in a minute. But we don't have to. So there's always an audit trail for as long as we want there to be one. And then the pending entries list. It allows us to know who's processing which message, how long they've been processing that message without an acknowledgement. If the worker fails, and we'll demonstrate this in a few minutes, if the worker fails, we can recover by looking at what was pending, process the pending messages first, and then move on to unassigned messages. Streams are easy to create. They're cheap. It's just another key, and we just create one. We can create as many as we want on the fly, as long as we're using reasonable constraints with CPU and memory. And in Redis 6 with ACLs, this also becomes a secure way of creating namespacing. One system creates its own delayed message streams, and nobody else knows about them. Nobody else can subscribe to them. No one else will be able to process those messages. All the rules around delayed eligibility inside of that system, in our case, in our communications system, are governed by that namespace. No one else has access to the Comm namespace, for example. Redis streams are cluster aware, so we have full reliability, and all the delivery management is built in. Now, one of the added hurdles to using Redis streams is cleanup. As I mentioned, we get the audit trail for free because nothing pops off the stream. The stream entries stay there until we remove them, which means that the streams will grow in size indefinitely unless we do something about it. And so we did this in two ways. The first way is to look at our time-based streams, the streams that contain the delayed eligibility messages. So for those, we set a TTL. We're creating them inside the system, inside, in this case, the communication system. And so we say, if we're creating a stream for application events, for example, that are delayed by 15 minutes in 1 minute increments, then those messages should easily have been processed inside of 24 hours. If something has failed, we will definitely have recovered it in 48 hours. And if there's any question about going back in time to look at an audit trail and getting it into our BI system, for sure, inside of 5 business days, that data, it has done all the work we needed to do with that data. So in our case, we set a TTL on all of those time-based streams for 5 days, and they get cleaned up automatically. No work to do. And so those are based on the last entry time. Every time we write into a delayed eligibility stream, we set the expire time to be 5 days in the future. So it'll be 5 days from the last entry written. Now, for those streams that are being processed immediately, there's no delay. We're just indefinitely processing entries to a stream. These we need to prune, but before a certain time. So what we want to do is give it an epoch time and say, get rid of all the entries in the stream that were entered before this epoch time. Now, Redis has a nice algorithm for xtrim, but it only does max length. I'm excited to see what comes next and when we get an algorithm for max time. Hopefully that's coming soon, but for now we implemented a Python script in this demo, for example, in our C# code. We have one similarly for C# called xtrim before that takes an epoch time, reads from the stream from the first entry until it finds an epoch time that's greater than the epoch time given, and takes that number of entries read, subtracts it from the total number of entries in the stream. That's our new max length, and we trim it to that new max length. So that's how we clean up our streams. So let's talk about our implementation and this demo. So for this demo, to demonstrate how low code the solution is, I ported all of our C# implementation to Python. Now it's not an exact port because it's for a demonstration, so there's a bunch of business logic that's missing that no one else has to worry about. Like it doesn't actually send email, so I just print a message that says email sent. But for the most part, the core pieces, the core components have been ported. And so we have an event producer that simulates the system producing events. In this case, we have 3 different events that we're producing: application events, decision events, and payment events. So the event producer is going to send those to streams named event application, event decision, and event payment. To simulate our customer communications system, we have a Comm event manager that's a multi-threaded script that runs an application event scheduler, a decision event scheduler, and a payment event scheduler. Those will make the appropriate decisions. Notice that the application events and decision events are delaying eligibility for processing, but the payment events are not being delayed. And then we have the email manager, which is also a multi-threaded script that runs 3 processors. I didn't give them their names here, but they're implementations of delayed stream processor group and then one of a Comm email processor script. Those are responsible for processing the messages in either the delayed eligibility streams or the Comm event payment immediate eligibility stream, and sending the appropriate emails either for application, decision, or payment emails. Let's talk about the code components. So we have a stream processor group, that's a class. We have a delayed stream processor group, also a class, and a third class called Comm event scheduler, which you probably could have named a little bit better to make it a little more abstract, but that's the scheduler. Now, to demonstrate low code, the stream processor group, which is responsible for all of the stream processing logic, is only 70 lines of functional code. It creates the consumer group if necessary. It ensures processing of pending messages first, so recovering from failure. It automatically retries if the blocking time expires. So if we don't use a blocking time of 0, and let's say it's 2 seconds, and we haven't seen a message on that stream in 2 seconds, it automatically releases and retries. It also determines if we process the stream to the end and then close processing of that stream, or we keep watching that stream indefinitely. So all that's happening in 70 lines of functional code. Now with the delayed stream processor group, with 50 more lines of functional code, we add the functionality of determining the next eligible stream name, waiting, if necessary, until that eligibility time becomes current. So if it's 12:05 and the next eligible time is 12:06, then we want to wait a minute until we can start processing that stream if it exists. So it does that. And it does all of this with 50 lines of code because it uses composition to include all of the stream processor group logic. Now with just 30 lines more code, we have the event scheduler, which is a subclass of stream processor group, and it's basically responsible for placing the messages in the appropriate streams. Now we do have 2 utility scripts, one Lewis script called end of stream, which is 25 lines of code, and this helps us determine if the consumer group has reached the end of the stream. This is really important. We're doing the delayed eligibility streams. First, it detects if the stream exists. If the stream does not exist, then we say it's reached the end of the stream and it returns true. Otherwise, it checks the last entry date or the last entry ID of the stream and compares it with the last entry ID delivered to the consumer group. If they match, it returns true. We also, as I mentioned before, have the xtrim before script that is 60 lines of functional code, and it prunes our streams down to the size based on the time, the epoch time we give it. To demonstrate how low code this can be, I just want to point out the application event scheduler as an example. It's a child of Comm event scheduler. And really all it needs to do is override the process message method. And the logic in that process message method has to determine one value, that's the number of minutes to delay. Because the Comm event scheduler does everything else. It determines the stream target name and the right formatting and places the message in the right stream. So this logic in this method can be as complicated as you need it to be. If it's based on information in the message stream, if it's based on any number of things. In this case, it's hard-coded to 15 minutes, but you can make it as easy or as complicated as you need it to be. And so the amount of code you have to write is really dependent on how complicated your business logic is. But you don't have to reproduce the scheduling logic or what the stream target names need to be. That's already done. So let's get into the demonstration. Let's see how this works. This is complicated to do live, right? I can't just do this live because we're going to have periods of minutes and hours between some of these events. So we're going to have to watch some static screenshots. So let's start off with a empty Redis database. So there it is. It's a local database. It's actually running in a Docker container on port 6300. So let's start up our event producer to simulate events coming out of the system. There's our event producer script, and we're telling it to produce messages twice a second. We don't need tons and tons of messages. We don't need to use up all the space. And so it's also running pseudo randomly. It's multi-threaded, and so we're running these 3 different messages. Events are being produced: application events, payment events, and then you see sometime later decision events. If we check in with Redis, we see that they've been published to the event payment, event application, and event decision streams. So there are our, which would be our typical queues. This would be the typical target of live events being published. And if we use a little script that we wrote just to check on those streams, we can see that sometime later we have about 300 messages in each of the streams, and then if we check a minute later, each of the streams has anywhere between 25 and 50 more messages. So the simulation of event production is working as we would expect. And so that's where we are. We're producing those events, and now we need to produce the delayed eligibility. We need to simulate what's happening in the customer communication system. So we do that with this multi-threaded Comm event manager script. It's important that we use a consistent consumer group and a consistent consumer name. This is particularly important when we're using things like automated provisioning systems like Kubernetes or whatever, Chef, Puppet, Ansible. We can't allow the workers to either randomly create groups or randomly create consumer names. That will eliminate a lot of the advantages of using Redis streams and consumer groups. We'd have to create some kind of a marshal to figure out what got left behind and reassign it to live nodes. So we don't want to do that. We want to make sure that if we're going to start up a node, that node uses the same group name and same consumer name each time. So however you do that with some kind of configuration system that you can figure out in your deployment mechanism. So when we start the manager, it's, like I said, it's multi-threaded, and it's going to process all 3 event types. And so because this is the first time we started the manager and the consumer group has never been created, it creates the group in all 3 streams. And it looks for pending messages first. There aren't any, of course, because this is the first time the group or consumer have been created, so it doesn't find any. So it transitions to adjusting to unassigned messages right away, and we start processing messages. It tells us that we're in a delay eligibility for 15 minutes and 10 minutes for decision events, but for payment events, we're not going to delay at all. And then we start processing messages. At 1352, this message was being processed, and it was delayed 15 minutes because it's an application message, and the eligibility goes into the 1407 stream. But for decisions, it's only being delayed 10 minutes, so this message that came in at 1352 is only delayed to 1402. And notice that the payment events are not being delayed at all. They're going into a Comm event payment, no delay. That's an immediate processing stream that will process indefinitely. And then we see our first acknowledgement that we processed, our first message. That's our payment message being acknowledged. Let's check back with the Redis database, and we can see that we do indeed have a Comm event payment, a Comm event application with a 1407 tag, and then we have the Comm event decision with the 1402 tag. Now, We talked a lot about recovery and how elegant this is. So let's kill the Comm event manager and sometime later bring it back up with the same consumer group name and same consumer name. And we see it looks to see if the group exists, and it does. So we just move on. And it says, okay, I'm going to start processing pending messages. And because in any kind of unexpected failure, you're going to leave messages in the midst of processing. You have to leave something. You get really lucky if you just happened to kill the process just as it just barely had acknowledged but not yet received new messages from the stream. So here it is processing those those pending messages. And eventually it returns to, it's now processed all the pending messages, and now we're processing unassigned messages. So now we're processing event messages into stream 1630, into stream 1625, and then of course into the Comm event payment stream with no delay. And there we are acknowledging that message. Now we can scale this horizontally. I won't show you all the gory details of spinning up 6 of these Comm event managers, but with each new manager process that we spin up, we give it a new consumer name. In this case, scheduler 6. So now we're processing these messages. I've simulated load on the processor that each of the message processing methods will sleep for half a second to simulate load of what it would take to, create an email and communicate with an email processing and get that email sent. And so if we want to process a ton of messages really fast, we just scale it horizontally, just spin up more of these processes. If this is Kubernetes, right, you just tell it to spin up more, and we get now 6, and we processed all of our messages 6 times faster, and now we've reached the end of the stream. So what happens if we've gotten to the end of all of the essentially cached messages, everything that has been sitting there? When we restart our event producer sometime later, we start seeing on each of the consumers, and we're not going to show all 6 of them, but scheduler 1 starts picking up messages at 16:51:59. Scheduler 2 gets it at 16:52:01. Scheduler 3 gets another message at 16:52:02. And they're just going to keep processing those messages and putting them into their delayed eligibility streams or putting them into the payment stream for immediate processing. And now if we look, we have a whole bunch of delayed eligibility streams and that Comm event payment stream. Now to note as we go forward that the first delayed eligibility stream for the decision events occurs at 16:21. And the first one for application events occurs at 16:26. So let's check in where we are in our diagram of our system. We've gotten the messages produced by our system. We've taken those and determined the correct delayed eligibility and put them in the right streams. And now we need to process those messages. We need to process the ones that are delayed for eligibility and the ones that are immediately eligible, and we need to start sending emails. So let's do that. We're going to use the Comm email manager script, which is also multi-threaded and has implementations of delayed stream processor group class and the Comm email processor class. So let's start that Comm email manager up. We'll give it again a consistent consumer group name. And we'll use consistent consumer names. We also need to give it a time to start. Remember that our first delayed eligibility stream was at 16:21, so we'll start just before that at 16:20. See what happens. We'll create that consumer group and the Comm event payment stream. It hasn't been created before, so we make it, and we start processing event payments right away. There's no wait, there's no delay. And there's the email sent for transaction ID 2306. The next thing that we see is that it wants to start processing pending messages for the event decision stream and the application stream that are delayed, but those don't exist because the first stream that exists for decision events is 1621, and so it says end of stream reached. And similarly, and it then says the next available window is 1621. That's the same thing for the application events, 1621. Now, notice that because the application event doesn't have a 1621 stream, it reaches the end of the 1621 stream right away and says, well, we're going to be looking for the 1622 stream next. And it'll keep doing that until it reaches the 1626 stream, which was the first one in the application stream series. But our Comm event decision does have a 1621 stream, and so it starts processing those messages, and there's our email sent for decision ID 2454. And we'll keep processing messages. Notice here that our application stream finally catches up to the 1626 delayed eligibility stream. It creates the consumer group and starts sending emails for application events. All along, we're processing payment events, and we're also processing decision events. Notice now, with so little code, we have a multi-threaded email manager, email processor, that's processing messages for decision events in the 1621 delayed eligibility stream, in the 1626 eligibility stream for application events, and for payment events, they're processing those events immediately, as fast as it can go, with just under 200 lines of code total. So what happens as we reach the end of the 1621 stream for decision events? It says, okay, we've gotten all the way. We've processed all the messages that are in this stream. This consumer group has gone from the beginning of the stream. We've processed all the way to the end of the stream. Nothing more can come into this stream because everything else that's going to be delayed will have to be delayed into another stream in the future. And so it says our resolution is configured to be 1 minute. So we'll look at the next minute's eligibility stream, which is 1622. And sure enough, there is a 1622 stream, and so it starts sending messages from the 1622 stream. Now what happens as we scale this horizontally, as we scaled the other manager, and we finally reach real time? We've caught up on all of our cached messages, and we catch up to real time. What do we see happening? Well, we simulated this to be in the middle of the night when, let's say, your users are not active, they're not submitting applications at midnight, almost 1 a.m., and they're not, so which means we're not getting decision events either. So as we catch up, the 12:52 a.m. stream didn't exist, so we moved on to the 12:53 stream is next. But we are looking at that at 12:52 a.m. And so it says, well, we have to wait 35 seconds before we can look into that stream because that stream is not eligible for processing until 12:53. When 12:53 rolls around, we find out that there is no stream for 12:53, so we've reached the end of the stream. Look at 12:54. Well, it's 12:53, so we're going to wait 60 seconds. And we'll keep doing this until we start getting new messages. But let's take a step back and say, what happens if the email manager crashes? We lose all the threads, all of the managers crash, and we don't know, well, and without going into Redis and looking up, okay, which was the last message processed in which stream, and we know that, you know what? Yesterday afternoon, everything was hunky-dory. Let's just start back there. So we restart the Comm email manager with the same consumer group name, the same consumer name, And we started at the same time as before. We knew it worked, so what happens? Well, we know there wasn't a stream for 1620, so it goes right to 1621. We know there are messages in the 1621 stream, right? The decision events, Comm event decision 1621 has messages in it. But because of our end of stream Lua script, we know that this consumer group has already consumed all those messages. So it just skips them and goes on. And it'll just keep happening, and it'll skip over all those streams until it reaches messages that have not been processed. So what happens when the dry spell ends? In this case, what happens when we restart the event producer? Now at 1:24 simulated time in the morning, well, the payment events immediately start processing, right? The manager's been processing those, and it puts it into the immediate processing stream, Comm event payment, and so those payment events get processed immediately. But sometime later, right, at 1:25, the first event decision delayed eligibility stream becomes eligible, and so we start processing those messages. So that's our demonstration. The series awareness, I won't go through the entire process of demonstrating all the scripts and what they do. I'll just demonstrate here how that works, because it's actually so simple, so elegant. And again, thanks to Redis for making this possible, and all the people who contribute to making Redis what it is. What we need to do is have a series-aware scheduler and a series-aware consumer processor. Now, how do I make that series-aware? In our case, because our events are linear, the customer has to apply before we can create a decision. We have to have a decision before they can submit an invoice. We have to have an invoice before they can sign a contract. We have to have a signed contract before we can activate the lease, right? These go in time linearly. And we've decided that the amount of delayed eligibility between those is fixed. It's 30 minutes. And we're not going to play with that. And so in our case, and in most cases where we have linear series like this, it's easy enough to use a counter. And so when the first event comes in, the application event comes in, we increment this counter. Now the counter is just a simple key in Redis that we've named Comm event series count. That's the prefix. And so every series counter will be named your namespace event series count. And then the series type. In this case, it's an origination series. We might have a different series when we're dealing with our merchant partners that we want to message to. That might be a different series type, or we might have a different series type for customers who are going through a different part of the lease experience. So here, this is the origination type, and we tie it to the customer ID because the customer, in this case, is the communication partner. In the merchant case, it might be the merchant ID. So here we have the Comm event series count. Origination is the series type, and the customer ID 1234. And so when we receive that application for customer 1234, we increment it from 0 to 1. Sometime later, but before the application eligibility has elapsed, we receive the decision event, and we increment the counter to 2. Now eventually, the application eligibility time elapses, and the processor that's aware of the series decrements the counter to 1 and says, well, that's not 0, so don't send the email. Sometime later, the event decision eligibility time elapses. It decrements the counter. It is 0, and so it sends the email. So without replaying all of that, it should be pretty easy to see that if the Comm event application eligibility time expires before we receive a decision event, maybe we needed more information from the customer, and so the application's in a pending status, waiting for them to send us more data. So we haven't performed the decision, so we haven't produced the decision event, 15 minutes go by, so the application event eligibility time expires. Now the counter is at 1 because we never received the second event. We decrement it, it's 0, so we would send the application email. And that's all there is to say about our demonstration and our implementation. In conclusion, I'd like to just point out again how low code this solution is, and all thanks to Redis. This is ideal for polyglot organizations where you could port this. We now have this in C# and Python. We'll be open sourcing those as soon as we can. You could easily port this, 200 lines of code. You can port this to Java or Rust or whatever your favorite language is, Node. And we're able to very elegantly produce a dynamic delayed message processing system and with series awareness. And again, this is RedisConf, and I really wanted to point out that this is all made possible because of the inherent properties of Redis streams and consumer groups. Thank you for your time. Again, if you have any questions or want to reach out, you can find me through the email that's shown on the screen or through LinkedIn. Thank you.